Okay, so lesson number 7 looks at interpreting statistical data using confidence intervals, levels, and margin of error. What we look at is how to interpret the data, not necessarily the calculations, but what does it mean when we put all of this information together. So in the past, when we looked at normal distributions, we looked at means and standard deviations from a population. So the question that they have here is probably not the best question for us. What is the mean height of all of the students in your school? We have a school size of less than 300. Realistically, it would be time consuming, but you could go through and you could measure the height of all 300 students. It would take you some time, but it could be done. If you go to St. Joe's, they have a population of over 1,000. You go to some of the schools in the city, they're more than 1,000. So when you have that many students trying to calculate the height of every, or measuring, taking the physical measurement of the height of every student would become so time consuming you wouldn't want to do that. So instead of instead of measuring the entire population, you would choose a sample size. So you would use a sample mean. The thing is, how can you be sure that your sample mean is similar to the population mean? So how do I know that the sample of students that I've chosen is going to actually give me an average that would match that of the population? So in that regards, with our school, if we were to take a sample to calculate the average height of the students in our school, remembering that we have little kindergartners all the way up to our grade 12 students, we would probably want to make sure that we were choosing students from every class, random samples, so that we weren't just choosing the tallest students, which could then make our results seem off. So when we take data from a sample and calculate the sample mean, we can't ever be sure that it's going to be the same as that of the population. But what we can do is hope that it'll be close to. The only way it's going to be the exact same as the mean of the population is if I actually took the entire population. So what we do is we determine a range of value around the sample mean in which we can be reasonably confident that the population lies in that. And if you look or listen to the election polls that are being done this month, you will see or hear those types of confidence intervals being stated. That when they make a comment that the PCs have this percentage of the votes with a certainty of this percentage, you'll understand what that means. So if the sample mean for the height of students is 67.5 inches, we can't be absolutely sure that the population is 67.5 inches. But we could be reasonably confident that the mean height would be between 65 and 70 inches. That was that with our standard deviation. We could be very confident that the mean height would be between 63 and 72 inches. So the range of values from 65 to 70 is called an interval. So I could be reasonably confident that the average of the students in the school is between 65 and 70 inches. I could also write the interval as 67.5 inches, which was my mean, plus or minus this margin or this flux of 2.5 inches. The 2.5 inches we call the margin of error. So I have an average of 67.5 inches, but it could be 2.5 inches above that or 2.5 inches below that if my calculations might have been a bit off. So if I had a range of values from 63 inches to 72 inches, what would be my margin of error? So to find my margin of error, I go from the mean, which was 67.5, to one of the two endpoints, either the 63 or the 72. So what is the difference between these two numbers? Calculate it for me. my margin of error would be 4.5 inches. We would be more confident that the population would be between 63 and 72 inches than we would be saying that the population was between 65 and 70 inches. The level of confidence that we have in a population that lies in a particular interval is called the confidence level, and we usually give it as a percentage. So we would not just say that we are very confident or reasonably confident. We would say that I'm 95% confident, or I'm 90% confident that the levels or the confidence level interval would be between these two numbers. So if we look at the next page, what percent of Canadian voters would vote for the Conservative Party? Again, it's not practical to survey the whole population. You're going to survey a sample. There's no way you're going to ask every eligible Canadian voting person the answer to this question. Because by the time you tabulated all the results, the election would have come and gone, and you have data that is no longer needed. So what you do is you collect a sample. Once you're done the sample, you might release this statement. In the poll, 38% of Canadian voters said that they would vote for the Conservative Party. The results are accurate within 3.5 percentage points 19 times out of 20, which means if I conduct this survey 20 times, so I take a sample 20 times, 19 out of those 20 times, I would have 38% plus or minus the 3.5. So over the course of those 20 different experiments, those 20 different surveys, I could be anywhere from 34.5 to 41.5 percentage points each time. So the margin of error becomes that plus or minus, that accuracy, and then my confidence level is that 19 times out of 20. So the confidence level is how many times you're sure it's going to happen. The margin of error is that flux between your average that you found in the survey, what the margin of error could be depending if I recreate this over and over. And then the confidence level is taking the 38% and adding the 3.5, that gives me the 41.5, or subtracting the 3.5, which gives me 34.5. So if we look at class example number 1, in order to determine the mean mass of golf balls produced at a factory, sampling is done.
Sorry for the interruption. Power School will be down again, so please shut down your Power School. Thank you.
So with this example, again, you would not take the mass of every golf ball that you produce because it's too time consuming. What you would do is you would then take a sample. So I grab a sample number of golf balls randomly. I take the mass of each of them and I repeat the experiment over and over. So the mean mass of golf balls produced at our factory is 45.6 grams plus or minus 0.3 of a gram, and the results are accurate 19 times out of 20. So the first thing that you're asked to determine is the confidence level. The confidence level is how certain are you that the results are going to be consistent. So how many times should this happen? So what is my confidence level? 19 times out of 20. What's that as a percentage? 95. So I'm 95% certain or 95% confident that the mean mass will be within this range. So my confidence interval is taking the mean and adding and subtracting the margin of error. So if I take 45 and 6/10 and subtract 3/10, what am I at?
45.9 and 45.30.
So my confidence interval would be 45.3 grams to 45.9 grams. What's my margin of error? So what am I off by?
6.
That's the whole part, but the margin of error itself is just the 0.3. So the margin of error would just be the 0.3. It's that plus or minus amount. How likely is it that the mean mass of golf balls produced at the factory would be 45.1 grams? What is the mean mass so far? What is the mean mass of my golf balls in this question so far? 45.6, give or take the 0.3. So my mean mass should lie between these two values. How certain am I that it's going to lie between these two values?
95.
I'm 95% sure.
So would you be 5%?
So the likelihood that it's not in these values is how much?
5%.
5%. So is it very likely? No. 95% of the time, the mass is between 45.3 and 45.9 grams, which is outside of the range. Or sorry, 45.1 is outside that range. Is it possible for the mean to be 45.1? Yeah, it's possible because I'm only 95% certain, not 100. If I was 100% certain that the mean lied between those two intervals, then the likelihood of the mean mass ever being 45.1 would be 0. It would not be likely at all. Okay. 2011 federal election occurred on May 2nd, and there were a large number of opinion polls that were conducted in the days leading up to the election. The table below gives the results of each of these polls. So there was the Harris Decima, Angus Reid, Nanos Research, and Ecos Research. These are all the research companies that were phoning residents across Canada asking them who they would vote for if they participated in the survey. The dates of the poll, the number of people they sampled, and then their percentage. Conservative, Liberals, NDP, Bloc Québécois, Green Party, and then what the margin of error is. So it says look at the columns for the number in the sample and the margin of error. So what do you notice about the sample size and the margin of error?
Margin of error is pretty small.
Okay.
Bigger samples.
When the sample size is big, the margin of error is small. Good. Okay. So as sample size increases, margin of error decreases. Any thoughts as to why that happens?
Because here, like, there's more to go over, so your percentage would be like stretched out.
Yeah, if you're sampling more people, you're actually, in a sense, getting closer to including the population. And the closer you are to the population, the more accurate your results are going to be when I compare it to the population. Because that's what this margin of error does. This margin of error takes the sample. So again, we're finding our 95% confidence intervals with the NDP party. So in the Angus Reid, what is my interval?
30.8 to 35.2.
And Nanos Research?
27.6 minus 30, or to 33.6.
And Ecos Research?
30,
Pardon?
33.
33 is the upper point.
Yeah. Lower, 29.4.
Thank you. So these are my confidence intervals for the NDP party. I can be 95% confident that between 26.9 and 33.1% of Canadians will vote NDP from the Harris Decima research, or 29.4 to 33.0 for the ECOS. So on the next page, we're going to take that chart that you just did and rewrite it in here. So that was 26.9 to 33.1, 30.8 to 35.2, 27.6 to 33.6, and 29.4 to 33.0. That's in the second column. So in the first column, what I'd like you to do is I'd like you to do the same thing with the 4 research companies using the Conservative Party. So you're going to go back to that chart on the previous page, and this time we're picking the Conservative Party, so it'd be 35 plus or minus 3.1, 37 plus or minus 2.2. So I want you to use those results to fill in the first part of the chart. Okay, so what is my confidence interval for the Harris Decima?
31.9 to 38.1.
Okay, Angus Reid?
39.2 to 34.8.
Nanos Research?
34.40.
To what?
40.
Sorry, I didn't hear you the first one. Thank you. And Ecos?
32.1 to 35.7.
So now what we're going to do is we're going to compare the results in each row. So if I look at the Harris Decima, 31.9, which is, we're just going to round that to 32, to 38. If I just put that on a number line, that would be those marks. Then if I were to put on the same number line the NDP, I'd have 26.9, which would be like 27, to 33. There's an overlap there. So these two results overlapped each other. If I look at the Angus Reid, 34.8, so that's just about 35, to 39.2. And then if I look at the NDP, I've got 31 to 35.2. So 31, to 35.2. Is there an overlap? Okay.
Yes.
If I look at the nanos, 34 to 40, and 27.6 to 33.6. Is there an overlap?
No.
No. Ecos, is there an overlap with the Ecos research?
Yes.
Yeah, because this goes up to 33 and this starts at 32. So there is an overlap. So the question asks, in which of the polling firms is there no overlap? That was with the nanos. Because there is no overlap between these two intervals, we can now be 95% certain that the results I get with the nanos research, the Conservatives will have more votes than the NDP. I cannot state that for certain in any of the other three polls, because in this poll, if I'm at the low end of my percentages for the Conservatives and at the high end for the NDPs could gain more votes. The only one that I can say the Conservatives have more votes is with the nanos, because no matter what, even at the low end, I'm greater than their high end. Does that follow? So then what I want you to do is I want you to look at the Liberal Party. So for Part D, you're going to do the intervals for the Liberal Party. So we have the Harris Decima, the Angus Reid, the Nanos research, and the ECOS research. So I want you to write out what the confidence intervals are for those 4 research companies for the Liberal Party. So with the Harris Decima poll, what interval did you get?
18.9 to 25.1.
Okay, Angus Reid,
16.8 to 21.2.
the Nanos,
19.7 to 25.7.
and the ECOS.
19.2 to 22.8.
Okay, so now let's look at the NDP results that you have up at the top of the page. I don't think I can scroll mine to catch those, so you'll have to just look up. Or can I? I can do this. Oh, not bad. There we go. Okay. With the Harris Decima, is there an overlap between these two intervals?
No.
Nope. Is there an overlap in the Angus Reid? What about the Nanos?
No.
And the ECOS? Is there overlap?
No.
No. So what we can say is we can be 95% certain in all the surveys that the NDP will receive more votes than the Liberal. Because I do not have a situation where there is an overlap. If there is no overlap, then I'm 95% certain that this party is going to beat that party. Because the highest this party is going to get is 25.1% of the votes. The lowest this party gets is 26.9. So it's still beating the other party. Okay, I'm going to skip question E because it looks at the same thing again, looking at overlap. We're going to look at the effective sample size. So suppose we go back to this question, the mean height of the students in your school. If I wanted to be 100% certain, I would need to measure every student in the school. That's not realistic. So instead I do a sample. The sample mean gives me 67.5 inches, and we have a confidence interval of 66 inches to 69 inches, where my margin of error was 1.5 inches. Now, if I had measured the heights of more than half the students in the school, my level of confidence that the mean lies between these two values would be quite high, probably above 99%. I could be 99% certain that my data is going to be true. If we did a quarter, my level of confidence would be high, but not as high as it was when I sampled a half. And then again, if I only picked a few students, my level of confidence would not actually be very high. So what this comes down to is if I fix my margin of error, I say my margin of error is 1.5 inches. The confidence level, so the certainty of which I can say that margin of error is correct, will increase as I increase my sample size. So this isn't talking like the other question previously looked at, the bigger the sample size, the smaller the margin of error. I'm talking about if I kept my margin of error the same, my confidence level, my certainty would increase as I tested more subjects within that sample. So a sample of 1,000 people is going to be more accurate than a sample of 500 people, which will be more accurate than a sample of 25 people. So the big thing that happens when you're looking at surveys, when you're looking at statistics, is you have to look at the validity of the statistic. You have to look at how many people were questioned. So I go back, my favorite one is the toothpaste commercials. Because every toothpaste commercial has 3 out of 4 dentists, or 2 out of 3 dentists, or 4 out of 5 dentists. When you start adding up the percentages, it doesn't make sense. How can 80% of dentists represent this brand, and then 75% of dentists represent this brand? It has to do with the sample size that they're taking. In the sample that they're taking, which conveniently enough happens to be all the dentists that I drop off samples to, they're recommending that particular brand of toothpaste. So you have to be aware of the statistic that you're looking at, because we can manipulate the statistic for whatever it is that we want to show. A company produces hockey pucks, and the league regulation says that the hockey puck has to be between 174 and 170 grams. The production equipment is set to produce pucks that have a mean mass of 170 grams, and the standard deviation has been calculated to 1.1. So if we assume that the pucks are normally distributed, that means that within one standard deviation, I would be between 68.1 and 65.9. Quality control testing is done to determine if the pucks meet the required standard. To ensure that only a small number of pucks produced are rejected, the quality control manager has to ensure that the mean mass of the pucks lies in the range of 66.7 to 67.3 grams. So what's my margin of error when we're talking about this? My mean average is 167, and I want my quality control to make sure that the mean is always between 166.7 and 167.3. So how does that differ from 167? 0.3. So I have a margin of error that is 0.3. So the margin of error that the company is using is 0.3 grams. The table below gives the sample size needed for different confidence levels. So if I want to be 99% certain of my data, I need to test 89 pucks. If I want to be 90% certain of my data, I test 36 pucks. and then the other two values are in between. So the confidence interval that the company is using for its quality control tests is what? What's the confidence interval?
Look at that, 166.
That's the confidence interval for the mean mass of the pucks. So it says how many pucks should be weighed if the company wants to ensure that this is correct 49 times out of 50. So 49 times out of 50 is what percentage?
So 98%.
So if I want to be 98% certain, how many pucks do I sample?
73.
Because a number cruncher has put this for me. So a number cruncher has said that if you test 73 pucks, I can be 98% certain that your mass average will be correct. Okay? So if I look at the next page. Pucks that don't satisfy the league regulations can still be used in practice. How many pucks should be weighed if the company wants to ensure that the mean mass is in this range 9 times out of 10? So 9 times out of 10 is what percentage? 90%.
36.
Because I don't have to throw out the rejected pucks. I just can't use them in the game. If the company was willing to accept a mean mass in the range of 166.6 to 167.4, would they need to test more or less pucks in order to attain the same confidence levels? So in this range, what happens to my margin of error? Does it increase or decrease?
It's great.
Okay, so the margin of error increases,
You have to do more pucks.
not more,
Less.
less. So the margin of error increases. So the sample size can decrease. The higher the margin of error, the smaller the sample size has to be. And the last question. A recent survey showed that Canadian high school students spend an average of 1.5 hours per day accessing the internet and 1.75 hours per day being physically active. The results are considered accurate to within 0.2 of an hour 24 out of 25 times. So it's 24 out of 25 times. Not 99%. 96. So this is my confidence level. So then I can say, so I can be 96% confident that high school students, high school students spend how much time per day accessing the internet? So now I have to state the confidence interval. So what would be the confidence interval for accessing the internet?
50.
That's the mean. What's the interval? 0.25.
0.25.
What's the margin of error?
Ah, well.
Look at the question again. What's the margin of error? The question doesn't say the margin of error is this, but it implies. What is the margin of error?
0.2.
0.2. Accurate within. So the margin of error is 0.2 hours. So what is my confidence interval accessing the internet? Take the mean and add and subtract the margin of error.
So 1.48 to 1.52.
No, this is 2/10, not 200ths.
Oh, right.
Do it again.
You got this one.
One point three and 1.7.
So between 1.3 and 1.7 hours per day accessing the internet. And how much time being physically active?
1.55 to 1.95.
And that's being physically active. So I have one more question for you. Could I then draw the conclusion that students, high school students, are more physically active than they are accessing the internet?
They overlap.
So can I say that they're more physically active? No, because there's an overlap. The 1.7 overlaps this range, which means that there could be some kids that are less physically active than they are spending time on the internet. So your questions 1, 3, and 4